Okay, so let's start with something like 7/8. Okay, so the question is, can I, without actually doing it, can we justify that 7/8 is a terminating decimal or not? Okay, so again, the trick is looking at that denominator. Well, 7 or 8 is really 2 cubed. So is there some way I can get a multiple of 10 in there? Yeah, I could multiply by 5 cubed over 5 cubed, which would give me 10 to the third power. So I could very easily convert that to a terminating form. So yes. What about 11 over 250? Okay, so let's think about how we can write our denominators, how we're making this decision. Not the numerator. No, we see 11. We saw 11 a second ago, and a second ago it was no, but this time 11's in the numerator position. Well, 250 is 2 times 2 times 125, which is 2 times 5 cubed. So is it possible for me to get a power of 10 in there? Yeah. If I multiply by 2 squared over 2 squared, I'd get some number times 10 to the third power. So this is another yes. It is possible to rewrite that fraction in a terminating form. Okay, what about 21 over 28? Okay, so again, the goal is to get it to say 10 to some power. This time, however, I want to look at the, well, so we start with the denominator is 4 times 7, and that's 2 squared times 7. Now, I could multiply by 5 cubed over 5 squared over 5 squared, which would give me some power of 10, but I have that 7 hanging around, so I have to be able to justify how to get rid of the 7. Now I'm going to look at the numerator. 21 happens to be 3 times 7, right? Now, what do you notice? You notice that both numerator and denominator have 7s, and so they can divide out, and I'm left with some power of 10 in the denominator, so that's a yes. All right, it seems like we're getting a bunch of yeses so far. Let's look at one more. Let's do 37 over 768. Okay, so our goal is to break this number up into its prime factorization and see if we can look at some power of 10. Well, let's just divide 768 by 2. So it's 2 times 384, and I can take another 2 out of that. So it's 2 squared times 192, and I can clearly take another 2 out of that. Seems like I'm just pulling 2's out everywhere. 2 times 96, and I can clearly take another 2 out. Yeah, it looks like we're going to go on for a while. So 96, 2 to the 4th times 48. Okay, we're getting closer. Divided by the, okay, 24, so 2 to the 5th times 24. Let's keep going. Okay, these are all our denominators, by the way. So I got 2 to the 6th times 12. Okay, now I'm starting to see a problem here. Yeah, let's just keep going. Divide that by 2, 2 to the 7th times 6, and divide that by 2, I get 2 to the 8th times 3. Okay, so notice I've just got this string of denominators. Where do we see the problem? Right? The problem is that 3, because I could very easily come in and multiply by 5 to the 8th over 5 to the 8th, which would give me some power of 10, but I have to justify that 3 dividing out. And if you look back at 37, 37 is a prime number. There's no factor of 3 in there. It's not divisible by 3. So I know, because I can't get that 3 out of the denominator, there's no way to express this in terms of powers of 10. So this is a non-terminating, it's not terminating. It's a non-terminating decimal. Okay, so it's our counterexample. Okay, so now that we've talked about recognizing terminating decimals, let's look at ordering them. How do we tell which one is bigger than another? And here's where we're going to take advantage of a fraction skill. So let me kind of give you an example here. So say I have 7 and 9. Clearly 7 is less than 9, right? In fraction form, 7 over 10 is less than 9 over 10. Okay, 7 tenths less than 9 tenths. Similarly, in decimal form, 0.7 is less than 0.9. Okay, but so this is our goal. This is what we want to do, is if I give you two decimals, we want to be able to identify whether the decimals are greater or smaller than one another. But notice the skill that we're going to take advantage of is this whole fraction idea, something we've seen before where I can compare fractions. So if I can get my terminating decimal in an equivalent fraction form, then I'll know based on the numerator which one in fact is bigger or not. Okay, so let's take something like 0.345 and 0.1474. Okay, different place values, but I can put them underneath, I can rewrite them under with the same common denominator. So over on the left side, right side here, sorry, that's 1474 over 10,000. 345, I can add a 0 to it, and that's 3,450 over 10,000. Okay, so now I've got the denominators to match, and I'm going to focus in on the numerators, and clearly 3,450 is larger than 1,474. Okay, so if I can, as long as I can get it to a denominator that has the same power, then I can do a straight comparison. Let me do one more with you. Let's do 0.0231 and 0.024. Right? Not the same number of digits, but the first one, the one on the left, would translate into 231 over 10,000. And I just need the one on the right to also translate into something over 10,000. Right now it's 0.024 over 100, sorry, over 1,000. So if I add another 0 here and another 0 there, I can see that I'm comparing 231 to 240, and clearly that one is less. So that's sort of the technique that we need to show students, is convert it to the same denominator and then compare the numerators to decide whether something's bigger or smaller.